So we're going to carry on where we left off. We were halfway through the proof of lemma 232. So what we were showing was that there are chunks of the universe which are models of all of the ZF axioms except for the power set axiom. So we fall one short. The idea is that we can look at those sets which are kind of intrinsically small. So we could pick some cardinal kappa greater or equal to omega, and we could look at the collection of sets which themselves have size less than kappa, but their members have size less than kappa, and their members have size less than kappa. So they're hereditarily of size less than kappa. And one way of just saying that is to say for a set X, its transitive closure has got size less than kappa. So we were in the business of showing that we were looking at these H kappa sets here, and that was defined to be the collection of sets X with a transitive closure of X at size less than kappa, where we had that kappa was a cardinal. Singular or regular, doesn't matter here. And we'd shown that all axioms of ZFC, lemma 232 we were looking at, and that's going to show that for regular kappa, right, then all of the axioms of ZFC will hold in H kappa. Indeed, it's true when kappa equals omega as well, right? Well, not quite, because of the axiom of infinity. But that will be an exercise. We only had to show that the axiom of choice, right, held in such H kappa. Okay, so let's do that. So suppose the range of F gives me a collection of non-empty sets, right? And F is in H kappa. So a particular domain and range of F is in H kappa. So all of those sets are small. We want a choice function. We want some G that will pick out for each set in the range of F. Here's the range of F. And here are typical things, objects in the range of F. Maybe this is some F of X, and here's some F of Y. What we want is a choice function some G which is going to take things with from the same domain of F, and what G of X will do is pick out a particular thing, and G of Y will pick out a particular thing. G of X in F of X here for any X in the domain of F. That's what the axiom of choice says. So if F is in H kappa, the domain of F here is in H kappa. Now, we assume that the range of F only has non-empty sets, so we can do some picking. Right, so that's what that says. Everything in the range of F is non-empty. And now, like we did for collection, we use the axiom of choice in V. Sorry, so use AC in V. Okay, I know I've got a choice function in V for this. There's certainly a choice function G for F with G in V. And now we just observe G is in H kappa. So really it's simple observation. Transitive closure of G is just a subset of the transitive closure of F. After all, domain of G is the same as the domain of F. And everything in the range of G is a member of the union of the range of F. So we're going to get this. But this has got size less than kappa because F is in H kappa here. So G has got size, transitive closure of G has got size less than kappa. So G is in H kappa. So it was simple. There wasn't anything else to do. Right? So that finishes that lemma. Okay. Right. Ask me anything if you want. Now the next little subsections I kind of covered a little bit. I talked about HF. These are the hereditarily countable, sorry, hereditarily finite sets. So they have the special designation HF here. And beware, of course, the subscript here says this is the strict upper bound to the size of the transitive closure of the sets in here. So everything in here is intrinsically finite. And then exercise 232, which I'll be setting for you, is saying show that actually V omega equals H omega. Okay. And what you do is, for showing that every set here is over here, you just show every Vn is a subset of H omega by induction on N. And then in the reverse direction, you pick something in here and you assume by epsilon induction, all of its members are over here. And then you deduce that the thing itself is over here. So those are reasonably simple inductions in each direction. Now, actually, HF is, again, it's almost a model of all of set theory. It's a model of the power set axiom, because after all, if this is the case, every Vn, its power set is there as well. It's Vn plus 1. So any x that's in here, its power set is in here as well. Its power set is there in the next level. So once we've shown this, it's clear that the power set axiom holds in HF. So actually all of the axioms of ZFC, apart from now, perhaps annoyingly, the axiom of infinity doesn't hold here, because here everything is finite. So it's a model of a kind of finite set theory, but there's no set of natural numbers here. There's no element of HF, which is the set of natural numbers. There's no infinite sets. So that's the basis of lemma 233. That all of the axioms of ZFC minus the axiom of infinity, I have to subtract that. And actually, for good measure, I can add in the statement that the axiom of infinity is false. Because that's true in here. There are no finite sets. All of these axioms here hold in HF. For all the other axioms, it's just the same argument that we did for H kappa. Okay. And the only wrinkle is that now we add the power set in, and we have to take the axiom of infinity out. (242) was about HC, which I already introduced. HC, also called H omega 1, this is the hereditarily countable sense. So the collection of sets whose transitive closure is countable, less than omega 1. Now, just as an application of the previous lemma, I know that all of ZFC minus holds in HC. So it's just a special case of 233. Just taking kappa equals omega 1. Again, don't get thrown by this. This is the strict upper bound, right? Here, everything is smaller than the suffix, so it's countable. Yeah. So some observations, right? Power set of omega is contained in HC. It's because any subset of omega, or omega itself, its transitive closure, if it's infinite, is omega. So it's countable and it would be in HC. So any x contained in omega has transitive closure of x contained in the transitive closure of omega. And so it's countable here. So every subset of omega is in here. So HC might be very large in terms of cardinality if this continuum is large. It might be that the continuum has got size out of 17, in which case HC is going to have size Aleph 17. Or it could be something even yet larger. So well, we have that omega is a subset of V omega. V omega plus 1 is the power set of V omega. So the power set of omega is contained in V omega plus 1. Just to remind us, it's that power set of V omega. So all the reals are in here. And HC is in here. I mean, all the reals are in here as well. But that doesn't mean that this equals this. HC is not contained in V omega plus 1 because there are all the countable ordinals are in here, whereas this has very few countable ordinals. For example, omega plus 2 is not in here, but it is in here. Any countable alpha is in HC. It is a transitive set, and it's got cardinality less than omega 1, so it's in here. But omega plus 2 is not a member of V omega plus 1. So HC contains, an awful lot of stuff, right? Which won't be here inside V omega plus 1. So omega 1 is contained in HC. But then again, if you look at the size of V omega plus 2, so this is the size of the power set of V omega plus 1. Right? And V omega plus 1 actually has size power set of V omega here, which is the size of power set of omega. So I can write this one down using cardinal arithmetic as 2 to the 2 to the omega here. So by Cantor's theorem, that's bigger than 2 to the omega. So Cantor's theorem says 2 to the kappa is bigger than kappa for any cardinal kappa. So this is bigger than this in cardinal arithmetic. That's over here. But this is the size of HC. So what we have then is that HC is not closed under the power set operation. This is what we saw for H kappas. In general, they're not closed under the power set operation. The axiom of power fails for the most general H kappa. So as we see, okay, H omega 1, which is HC, is not closed under the power set operation. Because here's the power set of omega. Omega is in HC, but the power set of omega is not in HC. Right? It's too big. Right? This is not a countable set. Right? It's too large. It's got size 2 to the omega. So it's too big. So the omega is in HC, power set of omega is not. Okay, are there any questions? So we're going to move on. Okay. So we've seen that so we've seen that there are these chunks of the universe that are models of the axiom. The say HC or HF or these H kappa sets, which are the class of things of limited size. So the idea is we just collect all these things of this particular size together, and we get a lot of axioms holding. What the next idea does, so-called reflection theorems, is say, well, in particular, I can always find a level of the V hierarchy that's a model of a particular axiom. Indeed, if you give me finitely many axioms of ZFC, I can find arbitrarily large V alpha, so arbitrarily large alpha, such that V alpha is a model of those axioms. Those axioms are true in those V alphas. So it's called a reflection theorem because the idea is you've got all these truths about V. We have the axioms of set theory are true in V, and we can reflect down to some level alpha any finitely many of those axioms and find this V alpha in which that particular prescribed list of axioms is true. So that's what we're going to be doing next, to see how to construct this reflection property. I mean, a comment also to make is, I mean, you may have noticed I emphasized finite collection of axioms. We couldn't do this with an infinite collection. I can't prove in ZFC, remember, that there is any structure in which the axioms of ZFC hold. Contradicts Gödel's second incompleteness. So I couldn't say, I'll take an infinite list of axioms of ZFC and find a V alpha in which all those axioms hold, because that infinite list could have been all of the axioms themselves. And there's no way I can prove in ZFC that there be a level V alpha in which those hold. So we restrict the theorem to just looking at finite lists of axioms. But in fact, the interest of the theorem is perhaps as much in its method as that result. It will have the knock-on effect later that we'll see that there's no way to formulate the axioms of ZFC using a finite set of axioms. You might wonder, when we listed the axioms at the beginning, I emphasized that we have these schemes. Various of the axioms are schemes: foundation, separation, replacement. You might have thought, well, if we were cleverer, we could perhaps replace those axioms, which were schemes talking about all possible terms, all possible functions, and so on. Maybe if we're clever, we could replace those with just finite axioms. But the reflection theorem will say, no, you can't do that. Right? So we're stuck with this particular viewpoint of set theory, we're stuck with having infinitely many axioms. Okay, so our next task is to look in 2.5. I'm going to remind us again about absoluteness, which I alluded to in chapter 1. Now we'll look at this in a lot more rigorous terms, I'd say, in section 2.5.1. We're then going to look at a criterion which is going to help us set up this reflection argument. And this is called the Tarski-Vort criterion. And it's just something general from model theory. It just says when collection of sentences is true in some structure, can it be true? Can that collection be true in a substructure? Right? So from a model to a submodel, structure, group to a subgroup. What makes, if I've got a collection of sentences true in a group, is there something I can say about the syntax there and the absoluteness to get that set of sentences true in a subgroup? So you can see the relevance to this. We talk about V and we talk about universes within V. How do I get downwards absoluteness? So let's look again at what absoluteness meant in terms that I mentioned before. So if you like to turn to 251, this is page line 911, you'll see the definition here. Actually, instead of me writing it all out again, I'll try and enlarge the camera on it and just talk our way through it. So what you should do is make me slow down and not talk too fast. All right, so so here I am talking about absoluteness. Sorry, just for a moment then, just to go back to paper for a second. What's the setup? 235, definition 235. What I've got is some W, class of sets, W, and W sits inside Z. Here. Now, for all intents and purposes, I mean, if you want as a first read through, you can take Z to be V, the universe of sets. But the proof is more general than that. So usually Z is V. And the idea is we may have gadgets inside W, right? And we want to know whether some formula, if this is true about the gadgets in Z, right? If and only if, or perhaps then that means that it's true about the gadgets in W. If this was the case, we'd say that the formula phi is downwards absolute from Z to W. If this holds for all parameters I could put into the formula from W, so then we say that phi is downwards absolute. From Z to W. So it's about sets in W. Well, it's about the formula and sets in W. Now, if I replace the arrow by one in this direction, so this is talking about downwards absoluteness, this we will call upwards absoluteness. We're going up from W to Z. So pick any vector of sets to put into the free variables of phi. If phi holds in W implies that it holds in Z, we'll say that phi is upwards absolute between W and Z. And the upwards absoluteness has to hold for all parameters at the same time. So let me write that out slowly. If for all x vector in W, phi holds of x relativized to W implies that it holds in Z, then we say phi is upwards absolute. from Z to W. And if both upwards and downwards absolute hold, then we say just simply absolute. So if it's both upwards absolute and downwards absolute, then we just say phi is absolute. Again, I would say upwards absolute between, sorry, absolute between W and Z. And as I say in the notes, if Z is V, which it often is, then we sometimes just omit mention of Z. We just say phi is absolute for W. That'll mean it's absolute between W and V. So that's shorthand there. So this is how a formula is absolute. Basically, we're saying its truth value about objects in W is the same interpreted in W or in Z, if it's absolute. So there's another notion, of course, which talks about not just formulae, but about terms being absolute. So think of a term as kind of defining an object. Formula might define a truth value, 0, 1, true, false for me. A term defines an object. And of course, if I define an object inside W, I might end up with a different result if I define it in Z. But an upwards absolute term, if I define something using that term in W, I then run the definition in Z, I get the same thing. So this is definition 236. So again, it's the same scenario. I got W contained in Z, and now I've got a term T. So term T is absolute for W and Z, if then the following holds. For any parameters I could put into the definition of the term. So maybe here. So for example, let T be a collection of X, such that X is a countable ordinal. If you want to think of this as being a concrete example here. So this is the set of countable ordinals. Well, omega 1 is the set of countable ordinals. So this is one way of specifying the first uncountable cardinal. It's this term here. But as we saw before, what's countable depends very much on what functions with domain omega you've got. Maybe W doesn't have all the functions with domain omega. So maybe W thinks there's some ordinals which are uncountable, which Z or V does think is countable. It's simply that W doesn't have that onto function. So then if I interpreted the term in W here, I might not get the real omega 1. May or may not be the true omega 1, meaning the omega 1 of Z, or V, if that's what it is. So T in omega here in W is simply just omega 1 in the sense of W. Well, if omega 1 in W was less than omega 1 of Z, I wouldn't say that the term is absolute from W to Z, because it picks out different things. T in W picks out this ordinal, which is countable in Z. If omega 1 of W is less than omega 1 of Z. T is not upwards absolute from W to Z. Okay, so this is an example, and it's illustrating the definition that I didn't finish. Here we're talking about a term being absolute. Well, it had better be that the term always picks out something in W. If and only if, well, if I interpret in Z, it had better pick out something in Z. Sorry, Z here. And they better be the same thing if this is absoluteness. So, to just run through it, I define a term in W, and it gives me an object in W. Right? It's better be when I run the term in Z, I get an object in Z, and they have to be the same things. It's possible that a term defined in Z, right, it might be that that term doesn't define anything. It may just become vacuous in W. Right? But it better define something in both places, and they better be the same. Okay, are there any questions? That's kind of abstract, but this is a kind of canonical example here. So in general, this term is not absolute between classes W and Z. Right? It would be if we had equality here, but that might not be the case. So what we'll look at now is the kind of model theoretic criterion that I was talking about. So 237 here is just some nomenclature. A list of formulae, right, phi vector, let's say phi 1 to phi n, is, we call it subformula closed. And it means that for any formula on the list, any of its subformulae are also on the list. So of course a formula might be a disjunction. So that's saying that each of the two disjuncts is also on the list. And if the formula is an existentially quantified other formula, the other formula is also on the list. If every subformula of any phi k is also on the list. It's useful when the argument that's coming up, which you can think of as perhaps like a finite induction, is to always have on the list subformulae. So we prove something for subformulae before moving up to proving something for the formula. And the lemma here is let phi vector be a subformula closed list I've got W contained in Z, okay, be terms, not necessarily transitive, but often will be, and often Z will be V. So the following are equivalent. Phi, the formulae here on the list are absolute. Between W and Z. When does this happen? Well, when clause 2 holds. So that says, whenever I've got some, I'll try and stick with the same phi I, is there exists x phi j x y vector here. So phi j is a subformula of phi I, and it is one of the things on the list. That's why I numbered it with a j down here. And all the free variables of phi I are occupied by this y vector here. If the following holds, I look at all possible gadgets that I could put into the formula phi I. Yeah? Sorry, this is free variables. If there's some z that will make this true, so if there is an x in z, again, try and stick with the letters of the lemma. If there's a gadget in Z that'll make this true here, then there's a gadget in W here that'll make this true. So it's a constraint on the existentially quantified formulae on the list. And if I satisfy this for all of these existentially quantified formulae, this will guarantee absoluteness altogether. Let me do 2 implies 1. So assume the criteria and let's get absoluteness. So we do by induction on the length of phi I. So I assume absoluteness is checked for all formulae on the list of shorter length. All formulae on the list of shorter length. In particular, for the subformulae here of phi I. And we now argue about what cases we may have here. Maybe phi I is atomic. But atomic formulae are absolute by definition. Right? If I have y1 equals y2, or y1 is a member of y2, this will hold here in W if and only if it does in Z. For gadgets from W. Okay. Suppose phi I is of the form phi j or phi k, so disjunction. By the inductive hypothesis, these are shorter formulae and are absolute. So the disjunction is also absolute. It'll hold in Z if and only if it holds in W. Right? It's just an either or. So the truth value of this just depends on the truth values of these separately. But these separately have got the same truth value in W as in Z. So does this. And if we've got negation, similarly. This is shorter than phi I. So phi j by itself is already absolute between W and Z. So it's got the same truth value in both places. So its negation does as well. So these are all kind of trivial. The only time something happens of interest is the final case. It says there is an x, so it's a phi j x y vector. So now we have to do something. We have to wake up and do something. Yeah? So we fix y vector in W. And what we want to show is that phi I is absolute with those parameters for its free variables between W and Z. So we write out here some equivalences. This holds here in W. Well, now I just write down what this is here. So this is just writing out what phi I is. Now relativize this to W. Phi j x y vector here of the matrix of the formula in W. So this is just the definition of relativization. This is a shorter formula, so I can use the inductive hypothesis. This is absolute between W and Z. And now I apply the criterion. Right? This way, if there is an x in W, so that this holds in Z, there's certainly an x in Z, because W is a subclass of Z. But the criterion is just what I need to write down this. If there is an x in Z, there is an x in W. There it is. That's why it's isolated like this, is just for this right to left here. So this here, since W is contained in Z, and this one by the criterion. Two. And this is just phi I y vector here in Z. So I've got absoluteness of phi I y vector from W to Z. So we're done. So this is absolute for W and Z. Here. That was 2 implies 1. I'll just crave your indulgence just to finish off 1 implies 2. Sorry, I know this is going over time slightly. So, but it's a 2-liner, right? We did the difficult stuff. We just see that the absoluteness allows us to say this. So again, we fix y vector in W. And let's assume that phi I y vector here in Z, let's assume it's one of these quantified formulae that we're interested in. Here. Sorry, I read these the other way around. Now we're assuming absoluteness here. So by absoluteness, I have phi I y vector holds in W, right? So there is an x in W such that phi j x y vector holds in W. That's just what phi I is. Phi I relativized to W is then this. By absoluteness of phi j, I can write here Z instead of W. So this here is then just what we want in the conclusion of 2 here. We want in the conclusion of 2 to be able to go from phi I in Z to there is an x in W such that phi j holds in Z. And that's what I've got here, right? From this, right? Phi I holding in Z to this. So this finishes this finishes the other direction as well. Okay, right, sorry that went on, but it was kind of silly to stop just at that point. Any queries? What I'm going to put up as exercises for, so Friday, I'm setting exercises on Fridays now rather than Mondays. So So this is about work we've done. Look at 231, 32, 33. Right, so, and this will be due next Friday. I'll put this up on the web page as well. That's the usual way of assigning the homework is on the web page, but I thought I'd clarify this again this time.